335 meters straight up. That is taller than the Eiffel Tower, taller than any skyscraper standing in Central Asia, taller than any dam ever built in the history of human civilization. And the country building it has a population smaller than New York City, an economy smaller than some American counties, a nation so poor that nearly half its income comes from workers sending money home from foreign countries. Tajikistan, a landlocked country most people cannot find on a map, and they are attempting to build the tallest dam the world has ever seen. The Rogun Dam, 335 meters of concrete, rock, and steel, designed to hold back an entire mountain river, a project so massive that its $8 billion price tag equals nearly the entire national budget. $8 billion from a country where the average person earns less than $4 a day. This is not just an engineering project. This is a nation betting everything it has on a single structure. If it works, Tajikistan transforms from one of the poorest countries on Earth into the energy powerhouse of Central Asia. If it fails, the consequences are almost too devastating to imagine. This is the complete story of how they are building it and why everything depends on getting it right. Join QuitTech Process as we take you inside every stage of this extraordinary project. But to understand why Tajikistan is willing to risk everything on this dam, you need to go back 60 years, because this story did not start with modern engineers. It started with the Soviet Union. In the 1960s, Tajikistan was not an independent country. It was a republic of the Soviet Union, a small piece of a massive empire that stretched from Eastern Europe to the Pacific Ocean. Moscow had a strategy: industrialize the remote regions, build massive infrastructure projects in Central Asia, dams, power plants, factories, transform these quiet agricultural republics into productive industrial zones. Soviet engineers fanned out across the region, searching for the perfect location for the most ambitious dam ever conceived, and they found it: the Vakhsh River, a powerful mountain river fed by glaciers high in the Pamir Mountains. The water crashes down through narrow valleys, dropping hundreds of meters in elevation over relatively short distances. The flow is enormous, the terrain is steep, the valley walls are solid rock. For a dam engineer, this was the Holy Grail, one of the only locations on the entire planet where a dam taller than 300 meters could physically be built. In 1976, the Soviet Union officially launched the Rogun project. The objective was clear: build the tallest dam in human history, generate enough electricity to power entire regions, control the Vakhsh River, and regulate water flow for millions of people downstream. Thousands of workers arrived. Camp counts were built in the remote valley. Roads were carved into mountainsides just to reach the site. Equipment was transported hundreds of kilometers over unpaved mountain passes. The work began, and for 15 years, the project moved forward. Slowly but steadily, the foundation of what would become the tallest dam on Earth began to take shape. And then, everything collapsed. In 1991, the Soviet Union dissolved. Tajikistan declared independence, but independence did not bring prosperity. It brought chaos. A brutal civil war erupted. The economy collapsed almost overnight. Government institutions fell apart. Funding for every major project in the country vanished. The Rogun construction site was abandoned. Workers left. Equipment rusted. The partially built foundation sat exposed to the harsh mountain winters year after year. Snow, ice, and water slowly damaged what had taken 15 years to build. For more than 2 decades, the tallest dam in the world existed only as a dream, slowly crumbling in a forgotten valley. Think about that. 15 years of work, billions of rubles invested, thousands of workers, all of it abandoned, left to rot in the mountains while a country tore itself apart. But the dream never died. And in the early 2000s, a new generation of Tajik leaders looked at their country and saw a painful reality. Tajikistan had almost nothing. No oil, no natural gas, no coal reserves worth mentioning, no manufacturing base, no technology sector. A landlocked country surrounded by mountains with almost no way to generate wealth. Except one thing: water. Mountains full of it, rivers carrying billions of cubic meters of glacier melt every year, rushing down valleys with enough force to generate enormous amounts of electricity. And sitting in one of those valleys was the abandoned foundation of what was supposed to be the greatest dam ever built. The decision was made. Tajikistan would finish what the Soviet Union started. They would complete the Rogun Dam, no matter what it took, no matter what it cost. But this time, there would be no Soviet empire writing the checks. Tajikistan would have to find the money itself. From a national economy worth barely $15 billion, they would somehow fund an $8 billion dam. The financial pressure is almost incomprehensible. This single project equals more than half the entire country's annual economic output. Imagine a family earning $50,000 a year deciding to build a $400,000 house with no mortgage, no loan, just their own savings and whatever help they could find. That is Tajikistan building the Rogun Dam. But the money was only one problem. The engineering challenges were even terrifying. Let us start with the most fundamental question. How do you build a dam in the middle of a raging mountain river? You cannot. The water would destroy everything. Every piece of equipment, every foundation, every worker would be swept away by the Vakhsh River's relentless current.
So before a single stone of the dam can be placed, engineers must first move the entire river out of the way. They do this by drilling massive diversion tunnels straight through the mountain, 4 tunnels in total, each one stretching more than 1 kilometer through solid rock, each one large enough to swallow the entire flow of the Vakhsh River and redirect it around the construction zone. Think about the scale of that. 4 tunnels, each over 1 kilometer long, bored through a mountain just so the riverbed can be temporarily dry enough to work on. This is not the dam. This is just the preparation to build the dam. 2 of the 4 tunnels were originally excavated during the Soviet era. When the project restarted, engineers found them damaged by decades of neglect. Water had seeped through cracks, rock had shifted, the tunnel linings had deteriorated. Every centimeter of those tunnels had to be inspected, reinforced, and rehabilitated before they could safely carry the river again. New concrete linings were poured, steel reinforcement was added, drainage systems were installed to handle groundwater pressure. The 2 remaining tunnels were bored from scratch, drilling crews working around the clock, punching through solid mountain rock meter by meter. The process is brutally slow. Hard rock mountain tunneling might advance only a few meters per day, even with modern equipment. But eventually, all 4 tunnels were completed. The river was diverted, and for the first time in decades, the valley floor where the dam would stand was dry. Now, the real work could begin. Before a single rock could be placed on the dam body, the foundation had to be prepared. And this is where most people have no idea how complex dam construction really is. The valley floor is not solid rock. It is covered in layers of weathered soil, loose gravel, and fractured stone that have accumulated over thousands of years. None of this material is strong enough to support a 335-meter dam holding back 13 cubic kilometers of water. Every bit of it had to be removed. Excavators scraped away layer after layer of weak material, digging down until they hit something that could actually support the weight: solid bedrock, ancient stone that had been compressed under the earth for hundreds of millions of years. But even solid bedrock is not perfect. Natural fractures run through it like invisible cracks in a windshield. Water can seep through these fractures, pressure can build behind them, and if water finds a path under the dam, the consequences would be catastrophic. So engineers drilled thousands of holes deep into the bedrock, some extending tens of meters below the surface. Into each hole, they injected high-pressure grout,
a thick cement mixture that fills every crack, every gap, every microscopic fracture, and bonds the broken rock into one solid, unified mass. This process is called grouting, and it happens across the entire foundation area. Thousands of injection points, millions of liters of grout, all of it pumped underground to create an impermeable barrier beneath the dam. Think about what is happening here. They are essentially gluing the inside of a mountain together, filling invisible cracks deep underground with cement to make sure water can never find a path beneath the dam. At the same time, a foundation drainage system was installed. Even with grouting, some water will always try to seep through. The drainage system captures this water and channels it safely away, reducing the pressure that would otherwise push upward against the base of the dam. This uplift pressure is one of the greatest threats to any dam. Water pushing up from below can literally lift the structure off its foundation. The drainage system ensures that never happens. While the valley floor was being sealed and strengthened, the mountain slopes on either side required their own preparation. The dam does not just sit on the valley floor, it connects to the rock walls on both sides of the valley. Those connection points, called abutments, must be absolutely solid. Any weakness in the abutments and the entire dam could shift or crack under the pressure of the reservoir. Workers scaled the steep valley walls, installing rock bolts, steel rods drilled deep into the mountain and anchored with resin, creating an internal skeleton that holds the surface rock firmly in place. Steel mesh was draped over the rock face to catch any loose stones that might break free. Shotcrete was sprayed over everything, sealing cracks and creating a protective shell. Drainage channels were carved into the slopes to redirect groundwater away from the abutment zones. Water is the enemy of every dam, and controlling it at every point of contact between the dam and the mountain is critical. Only after years of this preparation work, grouting, draining, bolting, meshing, and sealing, were the foundation and slopes declared safe enough to begin building the actual dam body. And the Rogun Dam body is unlike anything most people have ever seen. This is not a concrete dam. Rogun is a rockfill dam with a central clay core. That distinction matters enormously. A concrete dam is a solid wall of cement and steel that blocks the river through sheer mass and rigidity. A rockfill dam works differently. It uses hundreds of millions of tons of rock and gravel piled up in carefully engineered layers to create a massive embankment across the valley. At the center of this embankment sits the clay core, a thick column of specially selected and compacted clay that runs from the foundation all the way to the top of the dam. This clay core is the waterproof barrier. It is what actually stops the water from passing through. The rock on either side of the clay core provides structural support. It holds the clay in place, absorbs the energy of the reservoir pressing against the dam, and distributes the enormous weight across the foundation. Building this structure is a process of almost unimaginable scale. Rock and gravel are extracted from quarries near the construction site or transported from surrounding areas. Massive dump trucks carry loads weighing hundreds of tons each, making continuous trips from the quarries to the dam. The material is placed in thin layers across the dam footprint. Each layer is carefully spread, then compacted by heavy vibratory rollers that compress the rock and gravel into a dense, stable mass. Layer after layer, meter after meter, the dam grows. But it grows slowly. You cannot rush this process. Each layer must reach a specific density before the next one can be placed. If a single layer is not properly compacted, it creates a weak zone that could lead to settlement, cracking, or even failure decades later. At the center, the clay core is built simultaneously. Workers place specially prepared clay in thin lifts, compacting each one to extremely precise specifications. The clay must be at exactly the right moisture content. Too dry, and it cracks, allowing water to seep through. Too wet, and it becomes unstable, unable to support its own weight. Throughout this entire process, engineers continuously monitor everything. Settlement gauges track how much the dam body compresses under its own weight. core pressure instruments measure water pressure inside the dam structure. Inclinometers detect even the slightest horizontal movement. If any reading falls outside acceptable limits, construction stops immediately. The section is investigated, the problem is diagnosed and corrected before a single additional layer is placed. This is not construction. This is construction where the margin for error is essentially zero, because what sits behind this dam when the reservoir fills is 13 cubic kilometers of water. 13 trillion liters, enough water to cover the entire country of Luxembourg under 6 meters of water, enough to fill more than 5 million Olympic swimming pools. All of that water pressing against the dam with a force measured in millions of tons every single day for the next 100 years. If the dam holds, Tajikistan has a reservoir that can regulate seasonal water flow, generate electricity year-round, and provide water security for millions of people. If it does not, the consequences cascade downstream through the entire Vakhsh Valley and beyond. Cities, towns, and farmland stretching hundreds of kilometers would be in the path of the released water. That's why every layer of rock, every injection of grout, every centimeter of clay core matters. There are no second chances with a dam this size. While the dam body rises, the internal structures inside the mountain are being built simultaneously, and these internal structures are engineering marvels in their own right. The spillway system is designed to safely release excess water when the reservoir level gets too high. Without a functioning spillway, a dam can be overtopped during floods. Water flowing over the crest of a dam erodes the structure from the top down. For a rockfill dam, this is a death sentence. Rogun's spillway system includes vertical shafts excavated deep into the rock on the valley walls. These shafts connect to horizontal tunnels that carry water safely past the dam and release it downstream. Building these shafts required vertical excavation through hundreds of meters of solid mountain rock, section by section. Workers drilling downward section by section, installing steel reinforcement as they went, pouring concrete linings that must withstand enormous hydraulic pressures when water rushes through at high velocity. The tunnel structures connecting to these shafts were built in segments. Reinforcement cages were assembled inside the tunnels. Formwork was erected. Concrete was poured in carefully controlled sections, creating a waterproof, load-bearing lining that will last for the lifetime of the dam. The tunnel floors were finished with precision. Reinforcement and drainage layers were installed before the floor concrete was poured in measured sections. Every pour was tested for thickness, strength, and surface quality. These are not simple tunnels. These are high-pressure water conveyance structures that must function perfectly under extreme conditions for 100 years. A single weak point in a tunnel lining could lead to erosion that eventually compromises the entire spillway system. And then there is the powerhouse, the reason the dam exists in the first place. The Rogun hydropower plant is designed with 6 massive turbine units, combined installed capacity of 3,600 megawatts. That is enough electricity to double Tajikistan's current power output instantly. To put that in perspective, 3,600 megawatts is equivalent to the output of 3 large nuclear power plants, generated not by uranium, but by gravity, by the weight of water falling from a height of over 300 meters onto turbine blades spinning at enormous speed. The first 2 turbine units came online in 2018 and 2019. This was a historic moment. For the first time, the Rogun Dam was not just a construction site, it was a functioning power plant. Electricity flowed from the turbines into the national grid. Lights came on in homes that had experienced regular blackouts for years. Factories that could only operate part-time suddenly had reliable power. But more importantly, these first turbines allowed engineers to test the dam's systems under real operating conditions. Water flowed through the intake structures, through the penstocks and onto the turbine blades exactly as designed. Every vibration was measured, every temperature was recorded, every pressure reading was analyzed. The dam was performing. But the dam is far from finished. According to the current construction timeline, the dam body is expected to reach its full design height of 335 meters around 2029. But reaching full height does not mean the project is complete. The reservoir behind the dam will be filled slowly and cautiously over several years. You cannot simply let 13 cubic kilometers of water rush in at once. The weight of the water creates enormous pressure on the dam foundation and abutments. That pressure must be applied gradually, allowing engineers to monitor the dam's response at every stage. It is projected that the Rogun Reservoir will reach its maximum water level around 2036. Only then will the dam be operating at full capacity. Only then will all 6 turbines be generating their maximum output. From 1976, when the Soviets broke ground, to 2036, when the reservoir reaches full capacity, 60 years, 6 decades to build a single dam. Think about that. This project has already outlived the country that started it.
But the engineering challenges are only half the story. The financial and political pressures surrounding Rogun are just as intense. The total construction cost is estimated at $6.3 billion. For Tajikistan, this is not just a large number, it is an existential commitment. $6.3 billion represents nearly half of the country's entire gross domestic product. For years, the project suffered severe funding shortages. International donors were cautious. The World Bank initially refused to commit funding, not because the engineering was unsound, but because of political risks. The core concern came from downstream, Uzbekistan. Uzbekistan's agricultural sector depends heavily on water from the Amu Darya river system. The Vakhsh River feeds into that system. A massive dam upstream controlling the water flow raised alarm bells across the region. If Tajikistan holds water back during planting season to fill its reservoir, Uzbekistan's cotton fields could dry up. If Tajikistan releases water during winter to generate electricity when demand peaks, the flooding could damage downstream infrastructure designed for low winter flows. Water in Central Asia is not just a resource, it is a geopolitical weapon, and the Rogun Dam sits right at the trigger point. The World Bank eventually agreed to involvement, but only after demanding independent feasibility studies, comprehensive environmental assessments, and regional impact evaluations. The message was clear. This dam affects more than just Tajikistan. But despite the political tensions, despite the funding gaps, despite the decades of delays, Tajikistan pressed forward. Because for this country, there was no alternative. Without Rogun, Tajikistan faces a future of energy poverty. Winters where families burn furniture to stay warm because there is not enough electricity to heat their homes. Summers where farmers watch crops wither because irrigation systems have no power to operate. With Rogun, Tajikistan becomes an energy exporter, selling surplus electricity to Afghanistan, Pakistan, and China, generating revenue that could transform the national economy, providing reliable power to every citizen year-round. The stakes could not be higher. And Tajikistan is not the only country that has bet its future on a megadam. On the other side of the continent, China built something even larger. A dam that didn't just generate electricity, it reshaped the economy and the geography of an entire superpower. The Three Gorges Dam on the Yangtze River. Standing taller than a 60-story building, creating a reservoir so massive it visibly altered the landscape of an entire region. At full operation, capable of cutting 100 million tons of carbon emissions every year, regulating river flow for a region home to more than 400 million people. But the Three Gorges Dam was not built for electricity alone. It was built because the Yangtze River was killing people. In 1931, floods along the Yangtze killed more than 145,000 people. In 1954, the death toll surpassed 30,000.
In 1998, raging waters swept away thousands of villages, killed over 3,000 people, and caused tens of billions of dollars in damage. These are not distant historical events. These are catastrophes within living memory. Entire communities erased by a river that could not be controlled. China decided it would never happen again. They would build a wall across the Yangtze, strong enough to tame the most destructive river in Asia. The construction journey began in 1994, and the first challenge was the same one Tajikistan faced at Rogun, building a foundation strong enough to support something almost incomprehensibly massive. The Three Gorges Dam is 2,345 meters long, 181 meters tall, 115 meters thick at its base, a wall of concrete so enormous that the numbers almost lose their meaning. To support this mass, tens of thousands of workers excavated deep foundation pits, reaching down to layers of granite that had been forming for hundreds of millions of years. Each pit was a geological cross-section through the backbone of the Three Gorges Valley. Only solid, unfractured bedrock could support a dam of this scale. Every crack was mapped, every weakness was tested. A massive network of grout holes stretching thousands of meters was drilled and injected with cement slurry, bonding the fractured rock into a single unified block. Geotechnical sensors were embedded throughout the foundation, monitoring for any movement, any shift, any sign of weakness. This foundation had to be mountain solid, because the force pushing against it would be billions of tons of water every single day, forever. Once the foundation was ready, the concrete began to flow, and it never stopped. 20 tower cranes worked simultaneously, their steel arms swinging back and forth around the clock, lifting batch after batch of concrete into position. On the ground, mixer trucks and pumping systems delivered the heavy gray mixture in a continuous stream. The dam was divided into more than 230 pouring blocks. Each block received its concrete layer by layer. Every layer had to meet strict specifications for thickness, moisture content, and curing speed. Inside each block, a network of cooling pipes circulated cold water through the fresh concrete. Without this cooling system, the heat generated by curing concrete would cause it to expand and crack. Cracks in a dam are not cosmetic problems. They are potential failure points that could compromise the entire structure. Day after day, week after week, month after month, new layers of concrete were poured over previous ones. The dam rose tier by tier. By the time the final pour was completed, the total volume of concrete placed exceeded 28 million cubic meters. That is enough concrete to build a sidewalk 1 meter wide that would stretch around the entire planet twice. Think about that. Twice around the Earth, in concrete, in a single dam. More than 400,000 tons of steel reinforcement were tied together across 28 dam segments, creating an internal metal skeleton that gives the concrete its tensile strength. Without this steel, the concrete would crack under the enormous bending forces created by the reservoir. Expansion joints were strategically placed between segments, allowing the dam to expand and contract with temperature changes without cracking. Shear-resistant steel plates locked the segments together, ensuring the entire dam behaved as one unified structure under load. As the dam rose, it gradually tapered from its massive 115-meter base to a crest width of just 40 meters at the design height of 185 meters at its design height. Behind that wall, a reservoir capable of holding 39 billion cubic meters of water. Enough water to keep the Yangtze Valley safe from the floods that had killed hundreds of thousands of people over the past century. But building the dam meant moving the river, and the Yangtze is not a mountain stream. It is one of the largest rivers on the planet. 3 diversion tunnels were carved through the mountainside, each more than 900 meters long, 18 meters high, designed to handle flows of up to 11,000 cubic meters per second. During construction, more than 1.2 million cubic meters of rock were removed using drilling and mechanical cutting. No blasting was used near the foundation. The vibrations from explosives could damage the bedrock that the entire dam depended on. Once the river was flowing through the tunnels, the original riverbed became a dry construction platform, protected by cofferdams and high-capacity pumping stations that kept working conditions stable regardless of weather. And on that dry platform, the dam body rose, layer by layer, segment by segment, until it reached its full height and the reservoir behind it began to fill. Today, the Three Gorges Dam generates more hydroelectric power than any other facility on Earth. It protects hundreds of millions of people from catastrophic flooding. It has become the backbone of China's renewable energy strategy. But it came at a cost. More than 1.3 million people were displaced. Entire cities were submerged beneath the rising reservoir. Archaeological sites thousands of years old disappeared underwater forever. The Three Gorges Dam proved that a single piece of infrastructure can reshape the destiny of a nation, for better and for worse. And that brings us back to Tajikistan. Rogun is not Three Gorges. It is not backed by the second largest economy on Earth. It does not have unlimited funding or hundreds of thousands of workers. It is being built by a small, poor country with everything on the line. But the ambition is the same: control the river, generate power, transform a nation. The Rogun Dam, when completed, will stand taller than any dam ever built. Its reservoir will hold 13 cubic kilometers of water. Its turbines will generate 3,600 megawatts of electricity, enough to double the nation's power output and create surplus energy for export. But the challenges ahead are immense. Upstream, the glaciers that feed the Vakhsh River are retreating. Climate change is reducing the snowpack that creates the river's flow. The very water source that makes the dam viable is slowly disappearing. Downstream, Uzbekistan and other nations continue to watch nervously. Every cubic meter of water Tajikistan stores is a cubic meter that does not flow to their farms and cities. The geopolitical tensions around water in Central Asia are not decreasing, they are intensifying. Financial pressure never stops. Every year of delay adds hundreds of millions of dollars to the final cost. Every budget overrun puts more strain on an economy that was already stretched to its breaking point. But Tajikistan continues to build. Because when you have no oil, no gas, no coal, and no other path to prosperity, you do not have the luxury of giving up. You build, you farm, you sacrifice, and you hope that the engineering holds. The mountain is still there. The river is still there. And slowly, steadily, layer by layer, the tallest dam in human history is rising between them. Workers who started on this project as young men will retire before it is finished. Their children will grow up in a country powered by the dam their parents built. Their grandchildren will swim in a reservoir that exists because one small nation refused to accept that its future had already been written. The Rogun Dam is not concrete and rock and clay. It is the physical manifestation of an entire country's refusal to give up. And whether it stands for 100 years or 1,000, the fact that they built it at all is nothing short of extraordinary. If this story moved you, hit subscribe and turn on the bell icon so you never miss another incredible engineering story from QuitTech Process. We'll see you